Welcome back to class, everyone. If you haven't already, please take a moment to like my videos, subscribe to the channel, and follow the Labnato account. We have built our physical networks and connected our machines, but today we are looking at the brain of the computer. We are tackling CompTIA A plus Core 1 Objective 3.3 Demystifying RAM Characteristics. Today, we are going to learn how a system actually juggles the massive amounts of data flowing through it and how to select the perfect memory for any scenario. To understand RAM, you must understand the active workspace. Think of your computer's storage, your hard drives and SSDs, as a giant file cabinet. It is non-volatile, meaning it holds your data permanently, even when the power is off. But retrieving a file from a deep cabinet takes time. RAM, on the other hand, is your whiteboard. It is highly volatile. Data is written, wiped, and accessed instantly. But the moment you shut down the machine, that whiteboard is completely wiped clean. When we open up a desktop computer or a server, the standard form factor we use is the DIMM, the Dual Inline Memory Module. DIMMs are long memory sticks that feature independent electrical contacts on both sides of the module. To install them, you push them straight down into the motherboard slots until the catches at either end click securely into place. But what if we are working on a laptop? A full-size DIMM won't fit. We use the mobile standard, the SODIMM or small outline DIMM. These are highly compact alternatives optimized for tight spaces. Because laptops are so thin, you don't push a SODIMM straight down. Instead, you insert the module at a 45-degree angle and then gently press it flat until the side retaining clips lock it into the chassis. Before you touch any memory, you must memorize the golden rule of physical installation. Every generation of DDR memory features a precisely placed physical notch on its edge connector. This notch shifts its position with every generation. You absolutely cannot force a DDR3 stick into a DDR4 slot or a DDR4 stick into a DDR5 slot. The notch simply will not align. Tech tip: never use force. If the module rocks side to side, you are using the wrong generation of RAM. You'll hear the term DDR constantly. It stands for Double Data Rate Synchronous Dynamic RAM. In the old days, legacy systems transferred data once per clock cycle. DDR revolutionized this by transmitting data on both the rising and the falling edge of every single clock cycle. This effectively doubled the data bandwidth without requiring a faster clock frequency. Let's look at the generations you will encounter in the field, starting with the legacy standard DDR3. While completely obsolete for new builds, you will still encounter DDR3 in older office machines. It typically maxed out at 16 gigabytes per stick, pushing transfer rates between 800 and 2133 megatransfers per second. Next is the current workhorse, DDR4. This generation brought increased power efficiency and much higher density. A single stick can hold up to 32 gigabytes, and transfer rates jumped significantly, pushing 1600 to 3200 megatransfers per second. This is the standard you will see in the vast majority of enterprise desktops today. And now, the cutting-edge standard, DDR5. This is a massive architectural leap. A single DDR5 DIMM can support 128 gigabytes or more, pushing blistering speeds of up to 8,000 megatransfers per second. It achieves this by splitting the module into a dual 32-bit subchannel architecture, drastically improving data efficiency and reducing latency for modern multi-core processors. How do we actually measure memory performance? We look at two metrics. The first is transfer rate, measured in megatransfers per second, MTS. This is the raw speed of your highway. The second metric is CAS latency, which is the delay between the controller requesting data and the data actually arriving. The rule to memorize: higher transfer rates are better because they give you a faster highway, but lower CAS latency is better because it means less waiting. Even with fast RAM, we face a bandwidth bottleneck. A standard single-channel memory configuration utilizes a single 64-bit data bus. As modern CPUs evolved to process data incredibly fast, this single lane of traffic forced the CPU to sit idle, waiting for data to arrive. We needed a wider highway. To fix this, engineers added lanes to the highway using dual-channel memory. By installing two identical sticks of RAM, The system utilizes two separate 64-bit pathways simultaneously. This creates a massive 128-bit data bus, effectively doubling your bandwidth. This is exactly why RAM is almost always sold in matching dual-channel kits. To actually activate dual-channel mode, you must follow the rules. First, match your specs. The modules must match in capacity and speed. If you mix a fast stick with a slow stick, the motherboard will automatically downclock both to match the slowest module. Second, match your slots. Motherboards color code their RAM slots. To engage the dual-channel controller, you must place your identical sticks into the matching color-coded slots. For high-end workstations and enterprise servers, two channels aren't enough. These motherboards feature chipsets that support triple-channel, 192-bit, and quadruple-channel, 256-bit memory controllers. This requires installing 3 or 4 perfectly matched modules. If you miss a slot, the system simply drops down to the next highest supported configuration. But what happens in the real world if a technician messes up and mixes a $2 stick in slot A with a $6 stick in slot B? In the past, the system would fail. Today, modern Intel systems use flex mode. The system intelligently adapts, creating a fast dual-channel environment for the matching 4 GB, 2 GB from A and 2 GB from B, while the remaining 4 GB left over in slot B runs simultaneously in slower single-channel mode. Now we have to talk about stability. Believe it or not, background radiation, cosmic rays, and heavy electrical interference can literally strike your RAM and flip a single bit of data from a 0 to a 1. In a consumer gaming PC, this might cause a quick game crash, but in a Wall Street financial database, a single bit error can corrupt millions of dollars of data or trigger a catastrophic blue screen of death. To understand how we protect against this, let's look at the baseline. Standard consumer memory. This is non-ECC RAM. It is used in everyday desktops and laptops. It utilizes the standard 64-bit data bus, and it is unbuffered, meaning it connects directly to the CPU's memory controller. You will see this listed as a UDIMM. To protect critical servers, we deploy server-grade fortification using ECC, or error-correcting code RAM. ECC adds an extra 8-bit checksum to the module, creating a 72-bit data bus. The memory controller uses this checksum to detect and instantly fix single-bit errors on the fly, without ever crashing the system. If it detects a massive multi-bit error, it halts the system safely to prevent data corruption. To handle the massive electrical load of dozens of ECC modules, servers use registered memory, known as RDMs. An RDIMM features a hardware register chip right on the stick to stabilize the electrical signals. Here is your absolute compatibility rule for the A+ exam. You cannot mix ECC and non-ECC RAM on the same motherboard. Furthermore, you can never mix an RDIMM with a UDIMM. Here is your technician's checklist to study for the exam. Know your anatomy, DIMMs for desktops, SODIMMs for laptops, know the evolution, DDR3, 4, and 5. Understand optimization, utilizing dual, triple, and quad channels to increase bandwidth. And master fortification, knowing exactly when to deploy unbuffered non-ECC versus server-grade ECC memory. Let's put it to the test with a real-world scenario. Your client needs a RAM upgrade for an ultra-compact video editing laptop. They need maximum speed for rendering, but they do not need server-grade fault tolerance. What is the solution? First, because it's a laptop, the form factor must be SODIMM. Second, for maximum rendering speed, we choose generation DDR5. Third, to maximize the bandwidth highway, we configure it in a dual-channel kit. And finally, because they don't need fault tolerance, we save them money by specifying non-ECC memory. You now know exactly how to spec, optimize, and fortify system memory. Excellent work today. Let's hit the Hardware XP Boost Labs.